Welcome. Topic is stability of coordination compounds. Stability of coordination compounds or complex. Okay. So the stability of coordination complexes can be checked by two ways. That is, one is kinetic stability, coordination complexes, coordination compounds, and other cases thermodynamic stability, of coordination compounds. Okay, so first we will look on that kinetic stability, then we will go for the thermodynamic stability. Okay, so first is kinetic stability of coordination compounds. First topic is kinetic stability of coordination compounds. So for kinetic stabilities, what we will look that the kinetic stability means that kinetic means we mainly know that is the rate of the reactions. We will look that rate of reactions. Okay, so this rate here for coordination complexes, this rate can be explained that whether this rate is fast or not, that is explained by two ways. That is either that whether this is inert or labile. Okay, whether labile or inert. Okay, so this rate of reactions means that we look that whether it is fast or not, fast reactions or slow reactions. Okay, so that we can check by whether it is labile or inert. Okay, for labile, if the compound is labile, what we mean by labile? It means that for substitution the ligands are readily available, and for inerts, for substitutions the ligands are not available. It means that this is fast reactions and it is slow reactions. So we will look that for kinetic stability, we will look that rate of the reactions, so that the rate is fast or slow, that we look whether it is labile or inert. If it is labile, it means that the it is a fast reactions. Why? Because here that ligands are readily available for substitutions, and for the case of inerts, the ligands are not available. So this is the slow reactions. So kinetic means we look that rate of the reactions, and this rate of reactions can explain by labile or inert. Okay, for this labile and inerts, if it is labile, then that is fast reactions, and if it is inert, then that is slow reactions. So to explain this labile and inerts, we should go through that some mechanisms. Okay, for coordination compounds, some mechanisms we have to follow to explain that labile and inerts. So here mainly we look that substitution reactions. So these substitution reactions It means that what do you mean substitution reaction? That one ligand is replaced by another ligands, and these substitution reactions can be two-edged, or you can say that. What do you mean by these substitution reactions? Here that no change in coordination number, and you are looking for, let's say, substitution reactions of octahedral complexes. No change in coordination numbers and no change in oxidation state of metals. And here that one ligand is replaced by another ligands. One ligand is replaced by another ligands. This is the substitution reaction, and this substitution reactions we can explain by substitution reactions. Reactions can be two-edged. One is dissociative mechanisms, and another is associative mechanisms. Okay. And these dissociative mechanisms, what do you mean by these dissociative mechanisms? If we say that the dissociative mechanisms, this is one type of SN1 type reactions, and this is one type of SN2 reactions. Okay, and in this dissociative mechanisms, what we see here, that let's say any compounds Ml5X, this is that coordinate number 6 compounds, and if you do that dissociative mechanisms, then what happened, that dissociative means SN1 reactions passed, the leaving group will leave. Let's say this is leaving group, so this leaving group leave, it means that Ml5, after that nucleophile will come. Okay, then that will be that nucleophile Ml5. This is again coordinate number 6, and this is coordinate number 5. Okay, so this is that intermediate, and we see that in this intermediate, what we see that intermediate form with coordinate number 5. So these intermediates that can be either TBP, that is trigonal bipyramidal, or it can be that square planar. Okay, and if this is that intermediate, and this is the slow step. So we have studied in kinetic for writing that rate, but you look that is the slow steps. So slow step we will look, it means that rate is, let's say this is K1, then this is K1 upon this Ml5X. So this is the rate of this reactions. Okay, and now that intermediates can be TVP or can be square pyramidal, and that most of the cases it will be the square planar, and this is the very rare case, and this is the most of case. This is the most cases. Most cases we will get that intermediate as square planar, and very rare case we will get that intermediate as TVP in case of dissociative mechanisms. Okay, and these mechanisms we can explain either with by BBT and CFTs. Both the cases we see that whenever intermediate is formed, that is square planar and a TBP, and maximum case square planar will be that intermediate. And next we have that associative mechanisms. Associative mechanisms. And for this associative mechanisms, what we see here, let's say this is ML5X. So this is one type of SN2 reactions. SN2 reactions means that for living group will not live easily. Here both nucleophile and living groups are important. So first nucleophile will attack nucleophile and living group live at simultaneously at one steps. So it will be like this: ML5 here, X here, nucleophile. Okay, this is the intermediates, and these intermediates can be two things, that is PBP, that is pentagonal bipyramidal, or it can be that monocapped octahedral. So these intermediates, they sometimes will come in the exam. So what are the intermediate forms in case of associative mechanisms, and what are the intermediate form in case of dissociative mechanisms? And for that associative mechanisms, most of the cases intermediate form is BPP. So BPP, this is the most cases intermediate form is BPP. And monocapped octahedral, very rare cases it will form that monocapped octahedral. And here if I write that rate, so this is the slow steps forming intermediate, the slow steps. So rate is, we will write slow steps. Let's say this is K1, or let's say this is K2, then this is K2. Here nucleophile is there, nucleophile, and the living groups. Or I can write like this: nucleophiles ML5X. Okay, so this is that. So and how to write the rate, that is K2, and this is nucleophiles, and this one, this is the rate for associative mechanisms. And for this rate is only this and this. Okay, now we will explain that on the basis of we will use the two theories. One is BBT and other is CFT, to explain that whether it is labile or whether it is not, because for this kinetic stability we are studying that rate of the reactions. Okay, for kinetic stability means rate is high, means that is fast reactions. So that rate is explained on the cases of labile and inert. So we will look that rate of the reactions. For explaining the rate, we look the two theories, because we want to explain the rate. Rate means we want to explain rate whether it is fast or slow. That is explained by labile. Labile means fast, inert means slow. Okay, so for explaining the rate, we look the two theories. Two theories are used to explain the rate of the kinetic stability. of coordination complexes. And the two theories are, one is BBT theory, another is CFT theory. Okay, on that BBT theory, what you see that this BBT theory, this is 1 and this is 2. So we will use that two theories to explain that whether that coordinate compound is stable or not. The stable or not, how will you explain? Kinetic stability, we need the rate, and for rate we need that whether it is labile or whether it is inert. Okay, so this BBT, first we will go for BBT theories. For BBT theory, what you see that we will look that whether it is dissociative mechanisms or whether it is associative mechanisms. Okay, first is whether it is dissociative, whether the reactions is going through dissociative mechanisms or it is going through associative mechanisms. And if it is going through dissociative mechanisms, let's say it is going through dissociative mechanisms, then that we see that what are that intermediate has formed for dissociative mechanisms, that is TBP, another is square planar will form, and square planar is maximum cases. Okay, that I am not explaining again and again, but we have to remember that what are the intermediate will form. Okay, for dissociative mechanisms, but we will see that according to BBT, that inerts and labiles, because we want to study that kinetic stability. Okay, so that inerts and labiles, labile, it means that is fast reactions, kinetically fast reactions, and inerts, that is slow reactions. That fast reactions, labile and inert. Okay, so which reactions are labiles, fast reactions, and which reactions are slow reactions? Okay, so for kinetic stability, what we see that if it is fast reaction, then we can say that is highly kinetically stable, and if it's slow reaction, then that is kinetically slow reactions, because kinetic means we will look that rate. If rate is high, then that is a kinetically stable. Okay, so labels are fast reactions, it means kinetically stable reactions. Inerts, it is slow reactions, so it is kinetically less stable reactions. So this kinetically labile reactions for dissociative mechanism are labile are those, these reactions are those coordinations complexes which uses outer orbital complexes. So all outer orbital complexes type of compounds are labiles. So those coordinate complexes which uses outer orbital complexes are labile complexes. And for inerts, the complexes which use inner orbital complexes. Inner orbital complexes are inert compounds. So what do you mean by inner and outer orbital complexes? So we see that hybridizations for octahedral complexes, because here you are looking mainly for octahedral complexes, that hybridizations can be, that is sp3d2, or that is d2 sp3. So these are, here d is outer orbitals, so outer d orbitals, this is inner d orbitals. Okay, so whenever this outer d orbitals is used, that type of compounds are labile compounds, and whenever it use inner d orbitals, these compounds are inerts compounds. Okay, let's say if I take the examples, so you know that in chemical bonding, you know, where in which case it will use outer d orbitals, in which case it use d orbitals. Okay, 1 2 3. So in these compounds, like if I search, if that inner d orbitals, like here, that let's say our compounds are 1 2 3 4. If here, that is, if it is all are filled, then what we see that whenever you make the coordination compounds, like here that d4 cases, so if these are fully filled, then we have to use that sp3d2 and d2 sp3, the hybridizations. Since the two orbitals are not there, so we will use that, in this case, outer orbitals. So this is that inner d orbitals, and these are that, let's say here 1 2 3 4 5, this is outer d orbitals. Okay, so in this case, what we will use, this outer d orbitals will be used. Let's say, so if it is complexes with the d4, then here in this case, what we will use, that this will use. So this is sp3d2. So here that outer d orbitals is used. If the complexes, if it is using outer d orbitals, then this type of compounds are labiles. Okay, similarly this is inner d orbitals, and this is outer d orbitals. And now if here, let's say d3 is there, so now here that we can use that inner d orbitals also in this case. So if now that if I want to make the coordination compounds, then I can use this one also, means here. So here, by using this only, I can use the d2 sp3. So here inner d orbitals has used. It means that this type of compounds, if inner d orbitals is using, then this type of compounds are inert. Okay, so this what the BBT says, that if it is going through the dissociative mechanisms, first it has to go in dissociative mechanisms, then we will look at hybridizations. So if the hybridizations, if it is inner d orbitals is using, then that is inerts, and if it is using outer d orbitals, then that is labile compounds. Okay, this is the BBT explain if it is going through dissociative mechanisms, and if it is going through associative mechanisms, for that case labile and inerts can be explained. That is what he says, that for levels, if low lying vacant unhybridized orbitals are present, then the complexes for is labile, So if in a if it is low lying unhybridized orbitals, that is mainly d orbitals, is present, then that complexes is labile. And here if no low lying vacant unhybridized d orbitals, then it is inert. So we can explain that labile and inerts by looking at whether it has vacant, low lying vacants, unhybridized d orbitals present or not. If it is present, then that is labile, and if that is absent, then that is called inerts. Okay, so if I take that example, let's say example, if I take, let's say d orbitals, let's say d orbitals is there 1 2 3 4 5. So in hybridizations, again we look that hybridizations, let's say if that 1 2 3 let's say d2 is there. Okay, so for this, what we will do for that, we know that we need that when the hybridizations can be sp3 d2 and d2 sp3 for federal cases. So here that now if it is only d2, so here that sp3 for hybridizations, what we need, this is needed 1 2 1 2. So this is d2 sp3 d2 sp3. So here that low lying vacant unhybridized orbitals is present. This is low lying vacant unhybridized orbitals. So if it is present, then uh, that is labile compounds. Okay, now if now let's say in case of d d3 case 1 2 3 4 5, so 1 1 2 3. So in this case you see that if 1 2 3. Okay, now this hybridizations are like this. This is sp3 d2 sp3. So here that there is no low lying vacant unhybridized orbitals. Here that no, here that unhybridized orbitals like this is not present. So here no low lying unhybridized orbitals. So this type of, if this type of compound is forming, then that is total. So these are inert compounds. Okay, so we will look that whether that inner orbitals is present or not. Okay, like d3 here no have, it do not have. Similarly for d4, if you look there also, we will not have that 1 2 3 1 2 3 4 5 1 3. Okay, so if it is d4, let's say 1 2 3 4. So here we use that outer orbitals. So here also we see that for the case of d4 we use that outer d orbitals, then here that low lying is present. Just a minute. Okay, so yes, here that what you see, or I can make it more clear. If it is d4, okay, so here that is inner d orbitals 1 2 3 4 5, 1 1 2 1 2 3 4 5. Okay, now d power 1 2 3 and 4. So here that I will use that hybridization from here 1 2. So this is sp3 d2. So low lying backends unhybridized is present. Okay, low lying unhybridized present. So these are labile compounds. So here that for using that, you see that for me octahedral complexes 2d orbitals is needed. Okay, either from it may be from inner d orbitals, or it may be from the outer d orbitals. So if only one d orbitals, suppose in inner d orbitals only one orbital is free, then it will not use, because it need at least two orbitals. Okay, it need two orbitals. So if one orbital is there, then it will not use. So it will use outer d orbitals. This is inner d orbitals. So in this case, it use outer d orbital means one low lying vacant unhybridized is present. So in this case, this is also again that is labile compounds. And if it is not absent here, then these compounds are inodes. Okay, so we can explain that whether that is labiles or inert. Labile means that is fast reactions, inert means that is slow reactions. So labile means kinetically fast reactions, and inerts are kinetically slow reactions. So that we can explain by two mechanisms. We are mainly studying for substitution reactions. This is substitution reactions. So these substitution reactions can be dissociative manner, can be associative manner. That is SN1 substitution reactions, or can be SN2 substitution reaction. This is SN1 substitution, and this is SN2 substitution reactions. Okay, so that can be that dissociative means SN1 substitution reaction. So labile or inert, you can explain that for if it is going to dissociative mechanisms, then we will look that what type of hybridizations. So if it is using that inner d orbitals, then that is inerts, and if it is using outer d orbitals, then it is this is outer d orbital means that is labile. Okay, and for if it is using associative mechanisms, then we will not look that outer orbitals or inner orbitals. We will look that whether low lying vacant orbitals are present or not. Okay, that hybridizations can be outer orbitals or can be inner orbitals. It means that hybridizations, it may use outer orbitals or d orbitals. That is not a main point for associative mechanism. For associative mechanism, main point is low lying vacant unhybridized orbitals are present or not. For labels, if that unhybridized low lying vacant orbitals are present, then that is labels, and if it is not present, then that is inert. Okay, so some exceptions also there. Let's see that here you see that d3s are inerts, d4s are labile. If it is because it is using outer d orbitals. Exceptionals is there. Let's say if I say that d5 high spin. Okay, so d5 high spins means I'm talking about octahedral complexes. So here what you see that 2 3 and 1 2. So if I fill the electrons, then 1 2 3 4 5. Okay, according to BBT, 1 2 3 4 5. According to BBT, it says 1 2 3 4 5. Okay, this is inner d orbitals, this is outer d orbitals. So according to BBT, we see what that inner orbitals are fully filled. So if you do the hybridization, then I will do like this. So this is sp3d2. So this should be that no low lying vacant orbitals, no low lying vacant unhybridized orbitals. So this should be notes according to BBT. According to BBT, but experimentally it found that experimentally it is labile. Okay, so like that D5, like you can see that D6 high spins. So D6 high spin also it is not according to BBT, but it is labile according to that experimental found it is labile. Similarly, or I can write here exceptional cases. I will write here that are D6 high spins, another is D7 high spins, another is D9. Okay, we can also you can check it also. See that D6 high spins, that is labile according to that is inert according to BBT. Inert, we no need to remember this, you can check also. Okay, D7 high spins, this is also inert BBT. So how inert? Let's say we check that. This no need to remember, we can easily check it. 1 2 3 4 5 1 2. Okay, so you can see that D7, so 1 2 3 4 5 6 7, so no low lying vacant unhybridized orbitals is present. Okay, so this has to be that and it is, let's say it is dissociative mechanisms, and associative mechanism, then it is using that outer orbitals. The dissociative mechanism it is using outer orbitals, that is labile, but maximum case that ask that is associative mechanism. So low lying vacant orbitals, low lying vacant orbital we have to check. Okay, so here there is no low lying vacant unhybridized orbitals is present, so this has to be inert according to BBT, but experimentally found this is labile, this is also labile. Okay, so maximum we that mechanism is associative mechanism, so don't go through dissociative mechanisms. Maximum time this is associative mechanism, so we see that here that vacant and low lying vacant unhybridized is not present, so this is inert. Okay, according to BBT, and this is also inert according to BBT, but experimentally it found that it is labile and this is also labile. Similarly, we can check that D8 is inert, also here also inert, also here also according to experimental also that is inert. Okay, D8 that is inert, here also inert, but D9 here we say that this is inert, but experimentally it is labile. Okay, so all these things we will explain another theory, that is CFT theory. So let's go for another theory, that is crystal field theory. Crystal field theory, that is CFT. So interpretations of we are looking that whether it is labiles or inerts by using crystal field theory. First we look at BBT theory, then we are going for crystal field theory. Okay, so for this crystal field theory we again look for that is so this is sometimes important, that whether it is dissociative mechanism or associative mechanism. So you see that for dissociative mechanisms, what are the intermediates will form, that is TBP, another is square planar, and square planar is maximum cases. And for that associative mechanisms, that intermediates for it is that is BPP, and that is the maximum cases, and monocapped octaedral, that is the rare cases. Okay, so here also we will look that level and inots. I will look that level and inots. So for level we will look that if gain of CFSC during the reactions, then it is level. Then it is level. And if loss of CFSC during the reactions, then it is not. Okay, so we will look that we will not go through all this. We will go by a some clicks is there, so to calculate. And if it is also, we can check that if CFSC is gain, then like if we say that octahedral case, let's say this is the starting octahedral and its CFSC is, let's say, 0.6 delta knots. Then after reactions, let's say CFSC octahedral, after reaction CFSC is, let's say, 0.8 delta knots. Another case octahedral and its CFSC is, let's say, 0.4 delta knots. Then here what we see that from here to here gain is happened, so this is the gain. So here this is the level, and from here to here loss is happened, so this is a knot. Okay, so you can check that by checking that CFSC value whether it is gain is happening or loss is happening. From that we can check that whether the complex is labile or inert, means the reaction is fast or slow. Also another is there, trick we have to follow for that. Trick is if electrons enters in EG orbitals, means if electrons enter in EG orbitals, then it is labile, otherwise inert. And except, very important, except D8. Okay, because we see that D8 are inert compounds. For BBT also we see that are the inert compounds. Okay, so if that electrons comes to that EG orbitals, then that is automatically that will be labile. Okay, if electrons presents in EG orbitals. Okay, if electrons are present in EG orbitals, okay, that may be 1, 2, whatever. If electrons comes to the EG orbital, that will say if electrons enters in the EG orbitals, if electrons present in EG orbitals, then that compounds are labile. Okay, except D8. Okay, so we can check that for transition metal complexes, transition metal complex, what are there? We see that we have that either D1, D2, D3, D4, D5, D6, D7, D8, D9. Okay, this type of, either from this here to here, any of this will come for transition metal complexes. So if any one, so how will you check that whether it is labile or inert? So we will check that whether it is entering in the EG orbitals or not. Okay, so if it is entering in the EG orbitals, then that is labile, and if it is not enters in the EG orbitals, then that is not labile. Okay. And we also use that concept of BBT. So from BBT, what you know that from BBT, what you know that D1, D2, these are labile because here that low lying vacant unhybridized orbitals will present. Okay, because you see that 1 2 3 4 5, so here only 2 electrons, or it may be D1, on that case 1 electron. So this vacant unhybridized orbitals are present. So here is, so low lying vacant unhybridized present in D1 and D2 according to BBT. So these are always labeled. So D1 and D2 are labeled according to BBT. Now rest we will check according to the CFT. Okay, so CFT what says that if electrons enters, so from CFT, so both this concept we have to combine, and after that we will check that which are labile or not. Okay, so from CFTs what you say that if electrons enters in the AG orbitals, then they are labile, otherwise they are not. Okay, here from BBT low line vacant unhybridized orbitals, and from CFTs we look that whether electrons are enters in the AG orbitals or not. So we will check that D3 case. So if you check D3 case, so I will write here from CFT electrons enters in AG orbitals are labile. Okay, note that except D8. So we will check for all that. So D1 and D2 that is already labeled from that is BBT. So we will look next for D3. So for the D3 case we check 3. So here electrons are 1 2 3, so it is not entering in the AG orbitals. This is, so this D3 is, this is labile, this is not. If not enters in the AG orbitals, then that are labile not. If enters in the AG orbitals, then labile. If not enters, then this is not. Similarly, if you go for D4, 1 2 3, so in electrons D4 1 2 3. So D4 can be high spins or low spins. Okay, so if D4 is high spin, then it enters in the AG orbitals. Okay, then this is high spin, then this is labile. And let's say if D4 is low spin, on that case what you will see 1 2 3. So here 1 2 3 4, so no orbitals is entering in AG orbitals, so this is not. Okay, similarly we will go for D5 case. D5 high spins. So D5 high spins means that high spin means again it will enter here. So this is labile, or I can take this example again. 1 2 3. So here you see that electrons high spins, so 1 2 3 4 and 5, it enters in the AG orbitals. So this is labile. Similarly, if I go for D5, low spins, so you see here 1 2 3. So here we see that 1 2 3 4 5, so not enters in the AG orbitals. So this is again not. Similarly, we can go for D6 high spins. So here again you can look 1 2 3. So high spins means 1 2 3 4 5 and 6. The electrons enters in the AG orbitals, then this is again labile. means electrons are present in EG orbitals or not. If it is present, then that is a label. Okay, this is a label. And if we talk for these 6 low spins, then you see here 1, 1, 2, 3. So on this case, 1, 2, 3, 4, 5, and 6. This is EG and this is T2G. So here electrons are not coming in the EG orbitals, then this is again inert. Okay, similarly we can go for T7 high spins. Okay, so we can see that electrons are 1, 2, 3, 4, 5, 6, 7. So electrons are coming in the EG orbitals, and this is again labile. And in case of D7 high spin, select electrons 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7. So here also electrons coming in the EG orbitals, then this is also labile. Okay, similarly we can check for D8, that is the exceptional case. We have seen that this is exceptional case. Here also electrons will come in the these orbitals 1, 2, 3. Then let's see, this is high spins 4, 5, 6, 7, 8. So electrons is coming in the EG orbitals. So this should be labile, but we say that this is exceptional and it is not. Okay, this we say that this is the exceptional. Okay, so for both D8 high spins and D8 low spin also we see that electrons are coming in the EG orbitals, but it is exceptional, so we say that again 2, 3, 4, 6, 7, and 8. So EG is coming to that EG orbitals, so this should be labile, but this is exceptional, this is inert. Okay, at next we have that D9. Okay, this is high spins, so you check here that 1, 2, 3, 4, 5, 6, 7, 8, and 9. So electrons coming in the EG orbitals, so this is labile, or D9 or D9 low spin. So actually low spin and high spin is not applicable for D8, D9 cases. Okay, because both the cases will get the same things. So just I am doing here, but this is not applicable for D8 and D9. Okay, because both the high spin or low spin same electronic configurations you will get. Here you see 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, this is also labile. So what we see here, that for transition metal complexes we have the D1, D2, D3, D4, D5, D6, D7, D9. So from that we will check that which are labiles and which are inert, because transition metal complexes any one of these orbitals it will use. So if you know that all these things, then we can easily say that these complexes belongs to this orbital, so this is labile or this is inert, we can easily check. So first we will look that DBT, D1 and D2 are labiles, and other than that I say we can check that whether electrons are entering in the EG orbitals or not. For CFT, if enters in the EG orbitals, then they are labile, otherwise they are inerts. Okay, so I can classify that D1, D2, D3, D4, D5, D6, D7, D8, and D9. Okay, whether these are labiles or inerts, this one I can classify it two categories. One are labels and other are innodes. One is label, another is innodes. So you see that what are the labels and what are the innodes. So labels are, first one is, we can say that is D1 and D2. This is explained by BBT. Okay, and next, what are the labels? From here we check that if it is EG orbitals or not. If enters, then that is label. If not enters, then that are innodes. Okay, so from here we see that D3. First we check D3, that is innodes, not enters in the EG orbitals. So I will write here D3, that is innodes, and we can look. So D for high spin is labels and D for low spin is innode. Okay, so D for high spins is label and D for low spin is innode. Okay, now if you go for D5 low spin is innode and D5 high spin is label. Okay, similarly D6 low spin is innode and D6 high spin is label. Okay, so you can check here, that means that if it enters in EG orbitals or not. Okay, I am checking that electrons enters in EG orbitals. Okay, electrons entering EG orbitals, labels. Okay, so not that except D8. Okay, that I am looking here, and these are not entering, but this is equivalent to BBT, they are label. Okay, so after that I did these are equivalent to BBT. After that I am doing electrons entering in EG orbitals or not. So D4 high spins, D5 high spins, and low spins, D4 low spins, D5 low spins, and D6 low spins, and here D6 high spins, again label. Okay, now if you go for D7s, whether it is high spin or low spins, both the cases that is entering in the EG orbitals, you can check here D7. Okay, whether it is high spins or it is low spins, both the case it enters in the EG orbitals. So D7 is, whether it is high spins or D7 low spins, both the cases it is label. Okay, now we got if at D8, that is exceptional. Okay, it is label according to that concept, but exceptional, so this is innode for low spins and high spins. Okay, and low spin high spin is not valid for D8 and D9. Okay, so I will write here D8, that is innode, because this is exceptional. Okay, according to this concept, electrons enters in the EG orbital, that should be label, but we say that I said that this is exceptional, so this is innode. Okay, D8. Now D9 case, this is again label because electrons enters in the EG orbitals. So D9 case or D8 case, there is no low spin high spin concept, so I write directly D9. So these orbitals are labels and these orbitals are nodes. So if these orbitals are there, we can directly write these are the labels. If any coordination compounds, if they have the orbitals of this one, then they are labels, and it have this one, then they are innode. Okay, so we can easily so this is the combinations of this concept. We write combinations of both the concept of BBT and CFT. Okay, so both, if I combine the concept of the theories of BBT and CFT, I get that which are labile and which are innode. So the labile means that are the fast reactions, and these are the slow reactions. And slow reactions means kinetically less stable. This is kinetically more stable. Now also questions also asked that from this label also which is more label, and from this inot also which is more inots. Okay, these are the label, but now the questions it comes that which is more label. Let's say d1 is more label or d2 is more label. So from in between label which is more, for that also if questions is asked, then we have to look that orders. So from labels which are more labels, and from inots which are more inot, for that order what you look that for checking order of label or inots from label similarly order of inots from inots, what we do, we use the concept of JTD. Okay, so what the JTD says that doubly degenerates are strong JTD and triply degenerates are weak JTD. So strong JTD means more stable, so weak JTD means less stable. Okay, so for checking that from this level, if you want to check that which is more level, we use the concept of JTD. Okay, so now if I want to make this order from here, that which are that more labels and which are the more inots, what I do that let me make here. So we have that d1, d2, we have that d3, you have that d4, we have that d5, d6, d7, d8, d9, and we have classified that labile or inot. So labels are, what are that? So first equal to BBT, this is d1 and d2, and here comes d3. Okay, d3 equal to BBT, and electrons not enters in the edge orbitals. Okay, d1, d2, and so d4, that is high spins, d5, that is high spins, and here d4, that is low spins, d5, that is low spins. Okay, here d6, that is high spins, here d6, that is high spins, here that d7 high spin or low spin, both the case high spins or low spins, and d8, so d8 is exceptional, so it will comes here d8, and now d9. So these are the labile compounds and these are the inot compounds. But now we look that which is more labile. Okay, from this labile which is more labile. Okay, that order what we do, we use the concept of JTD. Okay, so what you look here, that order. Okay, so for that we look that first is high spin case, another is low spin. For that we need to separate it, that high spin and low spins. Okay, for checking the order. High spin. Okay, order of labile or inot, or so I'm checking that order of inot. I'm doing order of inots. Okay, if high inot means we can say that is low labile. Okay, so anyone, if you take order of labels, means high labile means low inot, and high inot means low labile. So I'm taking order of inotness. So in this case we can see that which are highly inerts. So for that we see that JTD concepts. Okay, JTD. So according to or we can check for order of, that is very easy, order of labile. Okay, so which is highly labile compounds, so that is strong JTT. The strong JTT is either that is, if that is doubly degenerates. So you see here that is D9 and D4 high spins. So if you draw the structure of D9 and D4, the past we look that strong JTT which we have. Okay, so D4 high spins, we see that 1 2 3 1 2. So here we see that high spin, so 1 2 3 4. So this is doubly degenerates. So doubly degenerate means strong JTT. Similarly, if you look for D9, that is high spin or low spins, similar to the configuration comes. So there is no concept of high spin or low spins. For this case, again, if you look 1 1 2 3. So here we see that 1 2 3 4 5 6 7 8 and 9. So if it is doubly degenerates, then that is strong JTT. Okay, so this is doubly degenerates, doubly, this is also doubly degenerate. Doubly degenerate means strong JTT, and strong JTT means highly stable. So we check here that for high spin complexes which are more, that is D9 and D4 high spins. These are that highly labile. Okay, after that, because this is explained due to JTD, that is strong JTD. Okay, now we will go for the triply degenerate is there. Triply degenerate means that is weak JTD, although that is JTD, right? So if JTD is present, then that is highly stable. So first we will look that doubly degenerate, that is strong JTD, and the triply degenerate is there, then that is weak JTD. So if JTD is present, that is stable, and if it has no JTD, means that is less stable. So first strong JTD we look, then we look that if any weak JTD is present or not. First JTD is present or not. So JTD may be weak and strong. So strong or highly stable. After that weak JTD will come, and after that no JTD will come. Okay, so if you compare the stable. So first we will look the strong JTD. Then let's look for any weak JTD is present anywhere. So then we check that D7 case. If you look, so if you look for D7 case, D7 case, okay, that is, let's say high spins 2 3. So if you peel the electrons, then 1 2 3 4 5 6 and 7. Okay, JTT is there, triply degenerates, and if you look at D7 low spins, then you look at 1 here, 1 2 3 4 5 6 7. Oh yes, that low spin case, that is strong JTT is there. Okay, but we are looking for the high spins. So for high spins, and also we have that low spin. Okay, so for high spins case, that is, this is weak JTD, because this is triply degenerate, and for low spin this is strong JTD. Okay, so we are looking first for high spin complexes. So this is weak JTD is there. So we look that D7, that is high spin. Okay, here I am written already high spin. Okay, D7 high spins. Another is Also it is found that according to BBT, this is nearly equal to 2, and BBT concept, this is nearly equal. Okay, D2. After that, so this is explained, this is explained by weak JTD, and this is BBT. Okay, now after that we will look whether any things, then we will go for, that is D1 will comes BBT. Okay, then what things has left? D1 I already used, D7 high spins I already used, D6 and D6 high spins. For D6 high spins, any JTD is there? Okay, D6 high spin. So you see that 1 1 2 3. Okay, so if I pull, then 1 2 3 4 5 6. Okay, weak JTD is there. So yes, it is found that D1 and D6 are equal, and this is weak JTD, and this is PBT. So D7 and D2s are equal, and that is a weak JTD, and this is weak, and these are the strong JTD, so that's why this is very high. Okay, this order. After that we will get D1 and D7, D1 has gone, then we have this I have used, this I have used, this is used, this is this, and this has left. So after that, what that order has found, that then we will get that D4, then we will get that D5. So this is the order for high spin complexes. Okay, order of level, and we see that this is the order of levels, and here that innotes, so I will add innote also, then D4 and D5. After that innotes will, which comes and D8 D8. So loss, this is for high spins. So high spin case, what we found that D8 and D3. Okay, so this is D8 and nearly D3. These are most innotes. Okay, D8 and D3. So now that is there, D8 and D3, and this is D6 high spins, so that I already used. Okay, D6 high spins. I am written here D6 high spins, D6 high spins, or this is low spins. I think innotes are for D6. Oh, set this is D6 low spins. This is the low spins. Okay, now so I have used that D6 high spins case, and D4 and D5 and D8 D3 I have used, D8 D3, then D4 and D5 I already used, then that high spins are which are left, D8 D3. These all are low spins, so I will not include this. So for high spins, that is D8 and D3. Okay, so for high spin complexes, these all are that high spin case. This is the order, and what we see here, So up to this, these are what you see the deeper the high spins, and after that this is greater than D7 and D2. So you see that up to this these are labile and these are inodes. Okay, and if I go for, this is the order. Okay, and if I go for low spin complexes, for low spins, if I talk about low spins, then I will order that order of labile. So these are all gone in the high spin. Okay, now I am going to compare for the low spin complexes. Then what will be the order? So most labiles will be, yes, D4 and D9s. So D4 for low spin, that is inodes. So labile will be only D9, because for D9 high spin low spin concept will not use. So first will comes D9s. After that, because of D4 low spins, that will be not, that will go on to inode. Okay, so I will not use. Then I will do, this is due to the strong DTD. Now next we have to go D7 and D2. Okay, so D7, if it is low spins also, that is strong JTD is there. Oh, I see. So D7, so D9, and after that D7 will come. Okay, that is strong JTD, and that is nearly equal to D2, and this is very stable complexes, because here 2 electrons will come in. Okay, why D9 is greater than D7? So you see that D9 case 1, 2, 3, this is, let's say, D9, and for D7 you see that this is also strong GTD, but you see that here electrons are here, that 1, 2, 3, 4, 5, 6, 7 and 8. Here 1, 2, 3, 4, 5. I'm using that low spin. Okay, sorry. Okay. So low spin, so 1, 2, 3, 4, 6, 7, 8, 9. Here 1, 2, 3, 4, 5, 6, 7. Okay, so here that what after JTT what will do, that one orbital is like this. So here that 2 electrons will come down and 1 electron over here, but here that 1 electrons only comes down. Okay, so it means that 1 electrons only release energy, so its energy is little less compared to this, although both are JTT. So this will be that highly stable, because strong JTT with that 2 electrons are reducing its energy. Here 1 electrons only releasing its energy. So this is have that high level. Okay, first is D9, after that D7 and D2. Okay, because D7 is due to strong JTT, and D2, that is for this BBT concepts. Next we will come that D1, and here D6 is there. So D6 low spins, that will be very inodes. Why? Because D6 there is inode come, so this is label will not come here, because that inode, and this D6 is highly inodes. The reason is that it has that fully according to BBT, what we say that 3, 4, 5, 1, 2, 3, 4, 5. Okay, so but that all electrons are fully filled, 1, 2, 3, 4, 5 low spins. So what is that? 1, 2, 3, 1, 2. So that low spins, that all are fully filled. So this is highly inodes, D6. So D6 will comes in the last, D6. After that we have that D8 and D3, and found that D3 is more inode than D8. Okay, found that D3 is more inode than D8. Okay, now so that is almost equal, but if you check from D8 D3 also, D3 is little bit more inode than D8. Okay, after that, sorry, this, okay, we are talking about a labile. So this, and after that what things has left? So I have used D7 D1 and D6 not will there here, in this case only D1. Then what things has left? D4 is there. Okay, D4 is there, D4 is there, D3 I have already used, D5 is there. So D6 I already used, D8 is there. Okay, so D1, after that we will have, and that is D4 and D5 is left. So after that we have that D4, then we have that D5. So this is that, the same way we can do this. So this is that order of labile if it is low spin. Okay, this is the order of labile if it is low spin, and this is also order of labile, and if it is high spin. Okay, so I'm erasing all these things. So this order we have to remember for labile and inodes, and this is explained by both combining the concepts of BBT and CFT. Okay, so this is that order of labels for high spin complexes, and this is the order of labels for low spin complexes. And we see that, and which are that labels here. So we see that which are labels. We know that from here, we know that this is label. So D9 and D7 D2 and D1 D1. Okay, after that this D4 D5 D6 and D8. So these are labels, and this is the order, and this is the actual label, and from here to here these are inodes, and this inodes, and this is the most inode, and this is the most label. Okay, similarly here this is the most labels, and this is the most inodes. Okay, so this way we can characterize, we can classify that labels or inodes from all these orbitals. Okay, if it's high spin or low spin, or simply also we can if that simply asks order labile and inodes, then we can easily classify that electrons enters in the EG orbitals. If it is entering in the EG orbitals, then that's the labels, and use that concept of BBT D1 and D2. Okay, so now that next small topics is left, that is, if it is given simply this, then we can easily characterize that which is labels and which is inodes. Now checking of labels, or now let's go for checking of inodes, inodness, or let's say I'm talking everything of labels. What that if this d orbitals, if electronic configurations is same, that is, let's say both the cases, I will look at questions. If both if electron configuration is same, then what, that levels is indirectly proportional to, that is, charge and A naughts are directly proportional to charge. That is, you say that if cobalt 3 plus and radium 3 plus, or we can mark this, and that question is, let's say example, chromium 3 plus and vanadium 2 plus is there. So both the case you see here also D3, here also D3. So both are D3, means D3s are inert. This is also inert. So but which is more inert? We want to check which is more inert. So that we see that inert is directly proportional to charge. So if charge is high, then that is more inert. So CR3 plus is more inert than B2 plus, because inert is directly proportional to charge. Okay, this is the one concept. If electron configuration is same, and also if electronic configurations is same and that charge is also same, like if we say that cobalt 3 plus, radium 3 plus, iridium 3 plus. In this case here also you see that 3d6, this is 4d6, this is 5d6. Charge is also same. Then if we check that inerts will be directly what we say that down the group inertness increases. It means that from here to here inertness increases. Okay, this is the second case. If both electron configurations and charge is same, and if electron configuration is same, then we look the charge, and if charge and electron is both are same, then if they have that different, that down the groups, then that down the group, their inertness will be. Okay, and the regions is simply that d orbitals down the groups, d orbitals are get diffused, and if diffused, then the overlapping will be the good. Or also we can explain that if the central atom size is big, then 6 ligands can easily bonded without repulsions, because central atom is more. Okay, that is explanations. Okay, and other cases is also explained that each for the case of isoelectronic cases, isoelectronic species means that electrons is same, like we say that LF6 P minus and SiF6 2 minus and pf6 minus E. All these cases we see that here the charge is x is 3, here x is, that is 4, here x is 5, and if say s of 6, that x is 6. So all this case order of liabilities will be what? That is, so that say that inertness is directly proportional to charge and level is indirectly proportional to charge. So if charge is high, okay, so here charge is high, so inert will be this, okay, and for level will be this, okay. For isoelectronic species, the isoelectronic species means same central atom have the same number of electrons, okay. And that last questions, that is